In the vast expanse of our solar system, an extraordinary scientific opportunity is about to unfold, one that promises to shed light on the mysteries of interstellar space. The interstellar object 3I Atlas, a visitor from another star system, has developed a striking ion tail as it nears its closest approach to the Sun. It's perihelion. By a remarkable stroke of sheer coincidence, two ongoing space missions, Hera and Europa Clipper, will soon pass through the region directly downwind of this tail. This incredible alignment was never planned. It is a purely serendipitous event, but it could allow us to collect the first-ever direct measurements from the tail of an interstellar comet, sampling material from far beyond our own cosmic neighborhood. In this video, we'll explore the full story of how this chance encounter came about, delve into why it's so scientifically significant, and consider what might happen next. A rare visitor from beyond the solar system. 3I Atlas is only the third confirmed interstellar object, a traveller from another star system, following the enigmatic 1I Oumuamua and the more conventional 2I Borisov. Its discovery earlier this year sparked immediate interest in the astronomical community. As it journeys closer to our star, the comet has been gradually brightening, a telltale sign of its icy composition reacting to the sun's warmth. As the intense solar heat vaporizes its surface, Atlas is venting a tremendous amount of gas and dust. This material forms a long, curved tail, a beautiful but ephemeral structure made of charged ions and water vapor. This tail is constantly being pushed away from the sun, carried outward across millions of kilometers of space by the relentless stream of charged particles known as the solar wind. At the same time, two completely unrelated spacecraft, Hera and Europa Clipper, are journeying through the solar system on very different but equally important missions. Hera, a European Space Agency mission, is heading toward the Didymos-Dimorphos binary asteroid system. Its primary objective is to study the aftermath of NASA's DART impact, a pioneering planetary defense test. Europa Clipper, a flagship mission from NASA, is en route to Europa, Jupiter's intriguing icy moon. It will perform dozens of flybys to investigate whether this distant ocean world has the potential to harbour life. By an extraordinary and unplanned coincidence, the flight paths of both of these sophisticated explorers are set to cross directly through the vast extended region of Atlas's tail. Hera's observation window, October 25th to November 1st. Europa Clipper's observation window, October 30th to November 6th. Researchers modelled the tail's trajectory using a tool called Tail Catcher, which factors in solar wind direction and speed to estimate how ionized material is carried away from the comet. According to these models, both spacecraft will pass about 8 million kilometers from the tail's central axis, far from the nucleus itself, but still within reach of dispersed charged particles. Of the two spacecraft, Hera is the less equipped for this specific task. It doesn't have plasma or magnetic field instruments, so its role will be primarily geometric and contextual. By precisely tracking its own location as it passes through the predicted tail region, it can help scientists refine the alignment and position of the encounter, providing a crucial reference point in space. Europa Clipper, however, is much better suited for the job. Its primary mission is to study Jupiter's moon, and it carries a sophisticated magnetometer and plasma instruments built to study Europa's environment. These sensitive tools could also detect the faint signatures of ions, plasma waves, and subtle magnetic field changes caused by the comet's interaction with the ever-present solar wind. The entire event will be brief, lasting only a few hours, and the solar wind's own variability could shift the tail in real time, making a successful detection challenging. But even so, the alignment represents a rare natural experiment. It's an unexpected and invaluable chance to study an interstellar visitor directly, using spacecraft that are already in flight for entirely different missions. Interstellar objects like 3I Atlas are snapshots of material from other star systems. Their chemical and physical makeup tells us what conditions were like where they formed. Until now, every observation of such objects has relied solely on telescopes. No spacecraft has ever directly sampled their surrounding environment. If Europa Clipper manages to record data from Atlas's ion tail, it would mark the first in situ measurements from an interstellar comet, a historic milestone. Even limited data could reveal how Atlas's composition compares with comets native to our solar system. The scientific goals: 1. Ion and plasma characteristics. Measure the density, energy and distribution of charged particles in the tail. 2. Magnetic field structure. Detect how the comet's interaction with the solar wind distorts magnetic field lines. 3. Comparative analysis. Determine whether interstellar comets behave differently from local ones under similar solar conditions. This encounter could also help refine theoretical models like tailcatcher, which predicts how solar wind shapes cometary tails. Somsigimebeban panasepens, sake isens ik tafkeseni, ten ananode dars, nenesen ans en neges taus ba de fudeni sedenberov. Never directly verified for an interstellar object. The spacecraft will pass far from the tail's core, meaning particle density may be low. The tail's structure could shift unexpectedly due to changing solar conditions. And because neither mission was built for this, scientists have little time to prepare. Yet even low-resolution data or null results would still be valuable. A non-detection helps set sensitivity limits for future encounters, defining what we can and cannot observe under similar circumstances. If Europa Clipper detects signs of Atlas's tail, it will be a breakthrough moment in space science, the first direct encounter with material from beyond our solar system. These measurements could refine our understanding of how interstellar comets interact with stellar winds, how their magnetic environments evolve, and what they reveal about the diversity of planetary systems. The insights gained here could guide future missions, like the ESA's Comet Interceptor, which aims to rendezvous with pristine comets or even new interstellar objects. Real-world data from Europa Clipper could inform its design, from instrument sensitivity to operational strategy. Time is short. Hera's contribution will likely remain positional, while Europa Clipper's team must configure instruments in advance to catch any potential signal. Afterward, scientists will compare the data to model predictions to refine our understanding of tail dynamics and solar wind interactions. Even if nothing is detected, the results will still shape expectations for the next interstellar visitor. This is a rare, unplanned, and extraordinary opportunity, a moment when luck and science intersect. If successful, Europa Clipper could deliver the first direct measurements ever made from the tail of an interstellar comet. Whatever the outcome, this encounter will redefine how we study and prepare for future visitors from the stars.